the topic moles that was introduced in Chemistry 1. So here's a brief introduction. So why are moles so important and where do they come in our lives? And we've got 6 opportunities there to pause this. And a mole is a quantity. So it's a specific number, just like a dozen, which is 12, a pair, which is 2. A mole refers to an exact number of anything. So we can have a mole of carbon atoms, just like we can have a dozen carbon atoms. We're going to look at particles, so it's going to include ions and molecules. And so for carbon and copper and water, in 1 mole there's always 6 times 10 to the 23 atoms, and we can be a bit more precise and we can put 6.022 times 10 to the 23, and here it's with water molecules. We've got a sample of 6 times 10 to the 23 carbon atoms. So how are we actually going to count that number? So it's actually the number of particles, here atoms of carbon, in the atomic mass of carbon, 12.01 grams, which you'll get from the periodic table. And for water, we've got 18.02 grams, which is going to be 18.02 milliliters of water, and they will still contain 6 times 10 the 23 molecules of water. And here's a mole of copper atoms, and the atomic mass is 63.56, and so just under 64 grams of copper is 1 mole of copper, and is the atomic mass of copper with 6 times 10 to the 23 atoms of copper. And so if we have a substance, sodium chloride, we would get its molar mass by adding 1 atomic mass of sodium to 1 atomic mass of chlorine, NaCl. And when we're making it here from the elements, we need balancing coefficients. And remember, whenever you don't have a number in front of a symbol or a formula, there's an unwritten number 1, a bit like x in algebra. What does the equation read? 2 atoms of sodium, 1 molecule of chlorine, gives 2 formula units of sodium chloride, Na plus Cl minus. Formula units because it's an ionic compound. If we multiply each of those coefficients by the Avogadro number, 6 times 10 to the 23, we end up with the ratio now in moles. So we have 2 moles of sodium reacting with 1 mole of chlorine to give 2 moles of sodium chloride. So the equation coefficients are really the amounts in moles. And so we're going to use information from the periodic table, and the larger of the 2 numbers given is the atomic mass, not always at the top number, but it's the larger of the 2 numbers. And you'll use atomic masses to calculate molar masses. And you're going to write the formula. So here we've got Mg2 plus O2 minus, so you've got 1 Mg ion to 1 oxygen ion, and so the formula is MgO. So you're going to add 1 atomic mass of magnesium to 1 atomic mass of oxygen to get the molar mass 40.31 for magnesium. But with copper sulfate here, you have to know the formula, and if you have a subscript, when you work out the atomic mass to get the formula mass, you need 4 atomic masses of oxygen actually in your atomic mass. And if we had hydrated copper sulfate, CuSO4.5H2O, And you need to be given that. It's not something you're born knowing. So if it's a hydrated salt, you include the number of molecules of water, and here it's pentahydrate because there are 5 of them. So you've got a mass of copper sulfate and you're adding it to a mass, 5 molar masses of water. So when you're working out the number of moles of a substance, you need to know the mass of the sample that you've got, the symbol or the formula, symbol if it's an element, formula if it's a compound, and the atomic masses of all the contributing atoms, or there we can have ions. So let's look at an example with bismuth. Incredible looking crystals of bismuth, a bit like a ziggurat. So what's its mass? You can see on the electronic balance there. The symbol of the substance and the atomic mass. Well, you probably don't need to know the symbol actually of the substance apart from identifying it on the periodic table, but you would need to know the formula if it were a compound. And so to get the number of moles, you're going to divide the mass of the sample by the atomic mass, and you look on the periodic table to get the denominator, the 208.98 for the atomic mass, and then you get the number of moles when you divide them through. So remember what you need, because you're going to watch a video, you're going to take the masses from the video and look at what the samples look like, and you'll need to know the symbol or the formula of the substance, the contributing atomic masses, to add them together to get the total molar mass, or just use the atomic mass if the sample's an element. I haven't given you a diatomic element. If it were O2, you'd have to double the atomic mass there. And here are some more worked examples, just to calculate molar masses of silver sulfate, aluminum hydroxide, and we have to write the formulas. And in fact, metal, non-metal there, for both A and B, they're ionic compounds. So we look at the ions and the charge on the ions to work out the formula. So Ag plus, SO4 2 minus, I need 2 Ag pluses, so that becomes the subscript Ag2, and the sulfate is SO4. Aluminum, Al3 plus, OH single minus, so I need 3 hydroxide groups for every one aluminum, so it's Al OH3. And remember that subscript 3 multiplies both of the atoms inside by 3, both the oxygen and the hydrogen. And then that's what we're doing here. We're adding each of the contributing atoms' atomic masses together. I need 4 of oxygen, I need 2 of silver in silver nitrate. In aluminum hydroxide, I need 3 oxygens and I need 3 hydrogens. And then we will sum the total to get the atomic, the molar mass of the material. And pause here, just calculate the molar masses of these substances. So you need to write their formulas. And look at number 5, it is a dihydrate. So the di is a Greek prefix there to tell you how many water molecules with each cobalt-2 chloride. And then once you've done that, once you've found the molar mass, what's the mass of a 1/10 of a mole of potassium carbonate? You've just worked out 1 mole. For part 6, you've worked out the molar mass of ammonium, and what's 100 moles. And then just a review. The mole tells you the quantity of reacting materials. Just like a dozen, a pair, it's an exact number, 6.022 times 10 to the 23 items, the Avogadro number. The molar mass is the sum of the atomic masses for all the contributing atoms or ions in the sample, and number of moles is the mass of the sample divided by the molar mass. And then, just in case you weren't sure where moles come into our lives, making plastics, so 1 to 6, you could have mentioned 6 different plastics, of course, because how much of each material are you needing in an equation? It's a mole ratio that's reacting. One of the largest amounts of inorganic chemicals that are used are acid, sulfuric and nitric, and you need to put the reactants for those materials together in mole ratios, and you can keep adding to what the mole is important for. But when we buy a material, someone else has done that calculation, but important to know where it comes from. And so thank you, Whiz Chemistry, for learning a little bit more about the mole, or reviewing a little bit more about the mole.